I want to take a little bit more time and to investigate a little bit more about this accumulating area that was, so this is an extension of the conversation in class. We're also going to look at a couple, maybe some more concrete examples as well, trying to help understand what we have here. So I have a little slightly different setup in this one than I showed in class. I have the A value set at 0. It doesn't have to be, right? I can move this about and obviously it would change the accumulated area. So here's a point on the function f, which is this kind of random cubic here that I could change, but some random cubic. And this point right here is the sum of the infinite number of rectangles from here to here. So it's that accumulated area. It would be this calculation. It's this number, okay? And so if I drag this further to the right, that point should go up because I'm accumulating more area. It's still going up, but not as fast, right? We should see there's a concavity change really happening in here, right? From concave up to concave down, because the rectangles, like think about like their heights are reducing. And then at this moment, we have now reached the maximum accumulated area. And these regions would have negative heights of those rectangles, so they're being subtracted off. And, you know, at some moment, the negative region would cancel out. This should be like all the way to here. So would cancel out that positive region, okay? So what we saw was when I would look at this whole graph, and if we would construct a tangent line right there, that there was a connection to this function. So I want to try to make that case a little bit more mathematical than just saying, hey, look, Sketchpad kind of shows it, because I don't know, maybe I was manipulating it, maybe I'm misleading you, so it's not true. But just wanting to maybe see this in a slightly different way. So I'm gonna go to here. Let me clear this off. I'm gonna maybe hide that function for just a second. So what I'm doing here is I'm setting the x, this initial value to 2, and then thinking about a delta x value of 0.5. And so if I'm moving from basically 2 to 2.5, we have accumulated more area here. That's all of this extra blue. And if we think about accumulating that, right, so I'm moving from 2 to 2.5, and so if I've done that, this point should go up equal to the amount of area that I just added. So it started here, it is now here. So this y value change should be this area, okay? So this y value change here, I've called delta capital F. So it's the capital F function. So just when you think about like delta y, change in y, right? Delta x, change in x. So I'm going to call it delta capital F. And it should be, you know, like the distance from here to here. But let's think about if I would take the derivative of this function, so this whole function. Well, the derivative of any function is the limit of the difference quotient. So if I go back to that definition, it's the limit as 2 points are becoming closer to 1 point, right, of like the change in the y values over the change in the x, its slope. And so I've written it actually here slightly different, just because I don't want h's. It's more of like the alternate form, if you remember that. But the limit as delta x approaches 0. So if delta x, which is actually here to here, approaches 0, shouldn't that point approach this initial point on the red curve, right? If I squeeze these back together, sorry, that shouldn't have moved. If I squeeze these back together, the two red points, like thinking about where it starts here to where it finishes here, if delta x goes to 0, that red point, we become 1 point, right? So we go back to that notion of derivative from first semester. Okay, so delta x is approaching 0, and this then is just slope, right? Remember that we're taking a secant line and we're turning it into a tangent. So delta y value for the red function, delta x value for the red function. So that is the derivative. So if I could calculate this, this should be able to tell me the derivative of the red function. So I asked this question thinking about little f. So this is little f, blue. And so I say, how can you define delta f, so the change in the y values here, in terms of f of x and delta x? How can you define delta capital F in terms of f of x and delta x? Now, you should keep in mind that delta x is going to 0. And so if delta x is going to 0, like if you look at this blue region that we have here, if I would zoom in on it, right, you're going to see segment, 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 and then you have this kind of curve, right? This is not going to be a trapezoid because the blue thing is not linear, right? It's not a triangle or not a rectangle. But if this delta x goes to 0, doesn't this side approach this side? And if those two sides approach each other, do you recognize that this shape is approaching, if this squeezes together, we are approaching really a rectangle. So this is a super exaggerated drawing, but if delta x is approaching 0, maybe imagine it even like this, but then even still smaller, right? Like, so it's got to keep squeezing down. So it really then would be the case that the change in the area that we're seeing, right? So the change in the y value from here to here must be the area of this tiny little rectangle as delta x approaches 0. So really, delta capital F is just f of x times delta x. Okay, if that's true, which it is, because I have my change in my height here should correspond to the area that I'm adding, and if my delta x again is going to 0, then the area I'm adding is really this rectangle, f of x times delta x. But if I substitute this now in here, look at what we would have. We would write the limit as delta x approaches 0 of f of x delta x over delta x. Do you see the 0 over 0 indeterminate form that we have right here? But there's a common factor. There's a whole, like we can see the delta x is common in the numerator denominator, which means, remember, this calculation here was supposed to be the derivative of capital F, right? It's the limit of the difference quotient. It's the limit of the slope of the secant line. And over here, this is what we're saying is equal to. Now, there's no delta x left once I've simplified it. So the limit as delta x approaches 0 of f of x is just f of x. So notice the red function is an antiderivative of the blue. It's not the antiderivative. I can't say that because of the plus c, right? There's a whole family of functions that are antiderivatives. Notice that in this case, if you look at my equation up here, that the c would be 0 for this one, that we're going through the origin. So that it's one antiderivative, but if there was a plus 2 here, we basically would be shifting this graph up, and it wouldn't change the slope conversation, right? But anyway, more on that here in a minute. So the red is an antiderivative of the blue, or the derivative of the red is the blue, and that is the right answer because any constant there would have dropped out. So again, the repercussion is that if I really want to understand this accumulated area, if I'm really trying to understand this shaded blue region here, I really only need to understand the difference of y values for the antiderivative. All right, I said I would try to make that a little bit more concrete, so I'm going to do that here. So I have a function. Now I've called it the derivative of capital F here in green, okay? So this is really like little f. Okay, so I have some function little f, which is 6x. Here is an antiderivative, right? It's an antiderivative that goes through a certain point. What point does it go through? 0, 6. Okay, maybe I wanted to go through that point. Or I just have an antiderivative. So let's see how this works out. So first, we know without the use of calculus that we can calculate the area of this green trapezoid. Okay, so pause the video, go ahead and calculate that for me. Should be simple, I don't care how you do it. So there's the function. Yes, please do it. So you should have just found, you have your bases here, you can plug those in. X is 3, right? If you didn't notice that, X is 3, A is 1, 1 and 3. So 1/2 base 1 plus base 2 times the height. Notice the height is really here, and you should have got the answer of 24. Okay. Now, a couple things. Making a connection here. So first, notice that if this connection exists between these functions, that means that if I would attach a tangent line right here, right? Think tangent line, I would take the derivative of that and I would plug in 3. Do you notice that that would be exactly the y value here, right? This is the derivative, plug in 3. So this y value would be 18, which should be the slope of that tangent line. So first, that's the relationship going one direction. So now going the other direction. Again, using what we know about this accumulated area. So first, notice it is not just the y value of the antiderivative at the same x value. So that would be 33. So this value is 33. And here's why that should make sense. Because different c values, right? If I change this to +5, I have not changed the derivative relationship between these functions, right? That's not any different because of the constant. So this y value really could be any shift, up or down. So it doesn't quite make sense then to think about that this signed area is equal to the y value of the antiderivative when this, I don't know which antiderivative I'm looking at, or there's many different antiderivatives. So when we go back to that other page, notice that it was the y value. It was the y value in this messy screen because this graph happened to go through 0. So then the accumulated area here would be equal to that y value. In this case, that's not true. But that's a really simple fix. And so when you think about this a value, really what we're looking for is that for the antiderivative, if this antiderivative went through that point, do you notice that the accumulated area then would have to be that y value? So let me say that differently, okay? So if we would find the y value on this antiderivative at 1, in this case, that's 8. So in some ways, this value of 8 is representing, like, if I would have started thinking about the amount that is accumulated from 0 until 1. And then so that region obviously then would have to be subtracted back off. And if this number is the amount that's accumulated really from 0 up until 3, so it's going to set us up to then simply subtract and really get the difference of these y values. So therefore, it leads us to this statement that the integral of capital F prime of x dx from 1 to 3 is the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. So in this problem, we would do 32 minus 8, which is 24. So if, again, I have a different antiderivative, notice it wouldn't affect this, because I've said repeatedly that the integral is the net change. So if the integral is the net change, again, shifting this graph, let's shift it like way up, like to 10. So what have I changed? I have now changed the y value of this point. I have changed the y value of this point. I have not changed the area I'm after, right? It's still 1 to 3. So if the connection between this point, the slope right here, should match the y value right here, that's still true. So it leads us to that conclusion of the relationship. So this relationship between these functions is still true. And therefore, any amount of area that I'm accumulating is really just the difference between the y values of this function. So, so as x would move from starting here at 1 and think about increasing it. Oh, it's not going to show that. Let me see if I can animate it. So it's not behaving the way I intended it to. So as this would increase from like 1 to 1.5 to 2 to so on, I'm accumulating more and more area. And so notice, like, if you go back and you set this maybe just to 1, the answer should be 0, right? Because we're really integrating now from 1 to 1, and we talked about that yesterday, is 0. So it wouldn't be the y value right here. That doesn't make sense to say what the accumulated area is. But again, that's why we're saying net change. So now if I go from 1 to 3, I need to take into account that at 1, there is no area. So now if I go to 3 and add this on, it should be not the y value here, but the y value here minus the y value here, because I know it should have been 0, because the integral from 1 to 1. So I think I said that better there at the last moment. So hopefully you followed that. Let's take a look at some, maybe just one other example here, looking at a couple functions, okay? So I have a sine function here. So here's the antiderivative. And so if I would think about drawing in, you know, some kind of x value here, like then having some shaded region. Let me maybe flip this around. Let me drag A about. Okay, so if I start here and I start dragging this, And if this is then thinking about like accumulated area, that's really what the red point here is representing. And I guess it's hiding it a little bit. And so we're expecting it here to come back down to 0, okay? So, and we see that. So we see this curve come up and then come back to 0 because we're canceling out, right? So if you look at the shaded region, adding area, adding area, adding area, still adding, but not as much, concavity change, maximum, subtracting area, subtracting area, subtracting area, subtracting area. So when I'm looking at from start to finish, here to here, we're really comparing the difference of those y values to determine our net change. Now, again, you might wonder, like, what is this curve about? Because I'm not really talking about it as I'm moving this. But notice that it is actually just another antiderivative, right? It's really this curve that we're constructing here for the accumulated area shifted, right? So there is some shift of this antiderivative that would cause it to match. And so then now as I drag this about, now it looks just like we would expect, right? So if I take it to like this moment and we think about what I'm trying to do to find this region. So we've argued now that it really should just be this y value minus the starting y value, because the starting y value would have an area of 0. Now, and that's true. So if I would find the y value of this point, and I know this one is 0, so we know the y value, like thinking of this antiderivative, I know the max, this max should be happening at where this sine curve goes back to 0, so that's pi. So cosine of pi is -1. So -1 plus 1 is 2. So this value then would be 2, which is going to make this value 0. So I know that this area in here should be 2. But if I would have a different shift, do you notice that the net change between this point and wherever I am now currently must be the same? It's really this height off of the x-axis to that max that we're just shifting around. And so it doesn't matter what this shift is, that we're going to get the same answer. So in other words, you don't need to know C, you don't need to know the constant to figure out this accumulated area. Because even though the constant here should have been 1 to make that look right, since it's the net change, it doesn't matter what it is, it's just a shift. Because again, the shift doesn't change the slope. So I hope that is at least a little bit helpful as we think about this. Let's maybe look at one more example here before we finish. Okay, so I have a function here. Again, I could call this little f of x. Often that would be what we would see. But I'm just emphasizing the fact that this is the derivative of some other function. So probably though the question would say f of x equals 1 over x. Find the integral. So this would say the integral from 1 to 4 of 1 over x, or f of x. So the integral from 1 over 4 of 1 over x. dx. Be sure you write that. So you can see the shaded region here. So we know that the function that's helping us understand this accumulated area should be the antiderivative of that. So I need the function so that when I would take the derivative, I get 1 over x. So hopefully you're already writing it down, the natural log of x. So again, I don't know what point it goes through, but it has some c value associated with it. And if we, so if I go ahead and maybe graph, so I'm going to plot a function here. I'm going to go ahead and graph the natural log of x, too many parentheses, plus some constant. And I'll just call it c, and I'll set the value to 1 is fine. Okay, so it's this. And so this value, let me change that color. This value, this of c, could be anything. There's nothing here that helps us understand it. I mean, it could be a half, whatever it is. So now, if this curve happened to go through this point, then I would know that this x, when I would drag it all the way back, there would be no area. So this curve is currently some shift of that curve that would go through that point. So really all I need is the y value on this new curve at x. I don't know why x is at 5 instead of... Yeah, I didn't click the button. Okay, so yeah, we're integrating from 1 to 4. I hadn't clicked that button yet. So I need to find the integral of 1 to 4, 1 over x. So I need to find the value of 4 on this function. Now you could say, okay, what if it does have the 0.5? It doesn't matter, because so let's do that. So I want f of 4. So we would write natural log of 4 plus c. Do I know what c is? Well, it's 0.5 in this case, so if you want to write that, you could. Then find f of 1. So that would be the natural log of 1 plus 0.5. And so if this is the value of 1 that makes the area equal to 0, it's kind of like this starting value that's going to have to be subtracted back off. So we would write the natural log of 4 plus 0.5 minus the natural log of 1, which is 0, plus 0.5. The 0.5's cancel, leaving us with the answer, the natural log of 4. Again, notice that it doesn't matter what c was. They would have canceled because we're finding the net change. It's the value that would have made that 0. So there's another example here for you in terms of how to calculate this. We could look at the graphs and these y values to confirm that, but I think this is a good stopping point here for us. So I hope that's helpful as an extension of our class conversation about finding this accumulated area under some function using that function's antiderivative.